My name is John Lobell. I'm a professor of architecture at Pratt Institute in Brooklyn, New York, and this is a sketch for a proposed lecture on genomic fabrication, making beyond 3D printing. So this could be any length, 15 minutes, half hour, whatever. And I'm going to be more lively in front of a real audience. So I'm just sitting in front of my computer right now. And the idea is that let's put together some things we've been thinking about. It from Bit, from John Archibald Wheeler, the genome, from Watson and Crick to J. Craig Fenner to CRISPR, a new kind of science from Stephen Wolfram, the game of life from John Conway, and the information is in the material. And that proposes a totally new way of fabricating and a totally new way of computing and a totally new way of thinking. So let's see what we're going to do with that. Again, this is very abbreviated. There have been 3 ways of making organic. When we think about Paleolithic, everything we made, we used our body. With the Neolithic, we get craft, where we can chemically change things like baking clay. And then the industrial mass production we associate with Henry Ford. And we're still doing that today. So if we look at how our smartphones are made, they're made essentially the same way Ford made the automobiles on the assembly line. But if you want to make an oak tree, you would not put a pole in the ground, nail sticks to it, and glue leaves to the sticks. You would plant an acorn and let the oak tree make itself. Why aren't we making our cell phones that way? And let's talk about how that could be coming about. Is this possible? So, it from Bit and Wheeler suggests that at base, all material is information. And that idea is developed by many other figures, including one of our favorites, David Deutsch, who talks about quantum constructor theory. As an architect, find that really cool. The genome. So, DNA, 4 letters, 2 rules, you make all of life. A new kind of science by Stephen Wolfram. How a set of rules can make richly complex things. Game of Life by John Conway. And here we see again a set of rules of which squares are white, or in this case blue. There are many gizmos made in Game of Life, and one of them is a glider gun. So here, this arrangement is manufacturing those little gizmos. Well, there we go. We are computationally manufacturing. We just need 3 more steps. Generate rich complexity, make it in 3D, and get it out of the computer into the real world. Which we put in quotes because what do we really mean by that? So, start with L systems or Lindemeyer systems, a favorite among architects. Very simple rule of dividing our line into thirds. Keep doing that. And you can make very convincing ferns and other plants that way graphically. So maybe nature's doing something similar. And the complexity. Well, here's a not too complex formula, giving us a Mandelbrot set, which we all know is infinitely complex. Just depending upon the power of your computer, you keep zooming into it, you still get more and more complexity. And let's just zoom in on that. And they have now zoomed in so far that when we're looking at one of these Paisley graphics, the original Mandelbrot set is larger than the size of the known universe. That's how complex you can get from that little formula. Let's see if we can harness that. You can make Mandelbrot sets in 3D and fractals in 3D, no problem. Here is zooming in on a 3D Mandelbrot set. Now let's look at getting it out of the computer and into the world. Maybe that's going to be a little more difficult. Here we'll turn to Neil Gershenfeld, director of the Center for Bits and Atoms at MIT. Gershenfeld begins by saying we all appreciate Turing, von Neumann, Norbert Wiener, etc., in creating the original architecture for the computer. On the lower left, we've got the von Neumann architecture for a computer: input, processor, memory, output. But we should be moving beyond that by now. For example, we start seeing the central control unit, or CPU, being emulated in memory, 1,000-fold speed up in computer, because you don't have to shuttle back and forth from memory. It's all there. Maybe there are other things we should be doing to our computer architecture. Why don't we look at nature, see how DNA does it? How do you build an oak tree or a human being? For one of the things is the information's in the material. It's not, in a 3D printer, you've got the computer, and then you've got the printer, and then you've got the material you're 3D printing. That isn't how life does it. So let's see if that becomes useful. Gershenfeld is looking at Lego blocks, the size of parts of electronic components, and then parts that can be assembled into making jet airplanes. Here's one of his students working on making airplanes out of nanocarbon, and he has set up fab labs doing this kind of assembly around the world, in particular in Barcelona. So if you think about it, okay, you go to school. I talk to students a lot, so you go to school to learn a skill, to make a living, to make money, to buy stuff. What if you just get a 3D printer and print the stuff? Skip the whole rest of it. And of course, way beyond 3D printing, that we can make things of great sophistication and do it because the information is embedded in the material. So what are some of the things we see going on? And of course, people have been working on related ideas in nanotechnology. Here's a little nanotech home assembler that can make you anything proposed. The nanotech people reject this genomic approach because it's not molecularly precise, which is important to them. But maybe these two should be getting together. Robert Freitas and Ralph Merkel have this book, Kinematic Self-Raplicating Machines. They have a massive patent on this kind of stuff, worth downloading and looking into their patent. We see self-assembly going on. IBM's using it for making chips. And we see architects using this. Here's Elisa Andrzejczyk using these kind of computational principles for making her architecture. Elena Mandelfini using them for fashion, for architecture. Peter Macapia using flocking software and making his architecture. Carl Schuh gives his students 3 genes, and by the end of the semester, the building has made itself. Haresh Lalvani, colleague of mine at Pratt Institute, explores what he calls the morphological genome, looking at the fundamental rules that can make all form, and again finding the information in the material. So these columns, which are in the Museum of Modern Art, take their form from the information not coming from the fabrication process from the metal itself, and then applying that to an apartment building. So we have used logic systems like Aristotelian logic and Boolean logic, but what happens when we start looking at the software our students are using, like Grasshopper on the lower left, suggesting totally new ways of thinking? Or on the lower right, we're looking at Stephen Wolfram's universe of possible universes, and he generates universes of possible logics. So this kind of thinking about totally new computer architectures could suggest not only new ways of making, but new ways of thinking. I try to track this on my website, Generative Genomics. Haven't updated it in a while, but there's more stuff going on. So maybe I should be getting back to it. Thank you.